explain this well. Let's say you wanted to find, I don't know, the acceleration due to gravity on Jupiter. You guys with me?
Yeah.
So, what's kind of interesting is the acceleration due to gravity. Like on Earth, it's 9.8 meters per second squared, right? And wherever you are in the universe, the acceleration due to gravity, for some reason in our universe, I don't know why, I can't explain it, but the acceleration due to gravity is always equal to the strength of the gravity field at that location. Are you guys with me on that? So, take here, Earth's surface. You're talking about an acceleration due to gravity of 9.8 meters per second squared. Those are the units, meters per second squared. And equivalent units are the strength of our gravity field here on Earth's surface, measured in newtons per kilogram. So it's like the same number, the same units. No, wait, it's not the same units. A newton isn't the same. Wait a second. A newton is a kilogram meter per second squared over kilogram. Okay? I just replaced newtons with kg meter per second squared. That's based on second law. Are you guys cool with that? I multiplied the units for m times the units for a. You guys good? So this, I'm just trying to show you that the units are equivalent. The units for acceleration are the same, equivalent, as the units for gravity field strength. Are they the same exact thing? No. And again, we don't know why. It's like the difference between inertial mass, which is the m in Newton's second law, versus gravitational mass, which is the m that you use when you calculate the weight of an object, the force due to gravity acting on an object. We don't know why those are the same thing. Those don't necessarily have to be the same thing in different universes, but in our universe, they're the same. You guys good? And so, I need you to look up something for me. All you need to find the acceleration due to gravity is you need the planet's what? What two things would you need? Let me draw it, and I think it'll become apparent. Let me add a page. All right. So I just added a page. Now here's an unknown planet. I'm gonna have you look up Jupiter, and I'm gonna have you look up the radius, the distance from surface to the center. Okay. So I'll write RJ, and you'll tell me what that is. What else do you think you have to know to figure out the gravity field? Okay, so you're going to look up mass of Jupiter in kilograms. You guys with me? So the way you would find, like this is for an object in free fall, right? So there's an object falling. Its weight is W. Okay. Can I use Newton's second law for an object in free fall? Is that constant acceleration? So I can use Newton's second law and say that the weight of the object equals to this net force, which has a magnitude of m times a. Are you folks good there? Because the net force has to be equal to the force due to gravity, which is the only force acting if an object's in free fall on Jupiter. So right now you're looking up the radius of Jupiter and the mass of Jupiter. When you have that, let me know. I got one more thing though. Universal law of gravity is Fg equals big G m1. So one of these masses is the planet. Can the other mass be can I call this mass m1? Are you guys cool with that? The one that's in free fall. So mass of the planet times m1 over r squared. And if I use Newton's second law, isn't net force equal ma? And this is m1 times a. Are you folks good? So I got m1 a Do you guys see what happens here? What happens to M1? It's gone, right? Divide both sides by M1, it's gone. So we get acceleration due to gravity, which, by the way, we call little g, right, if it's on Earth. But now we're talking about little g for Jupiter, so I'll write a little Jupiter there. And it's going to be g mass of Jupiter over radius of Jupiter squared. Did you guys get those numbers yet? All right. So what's the radius of Jupiter, please?
It says mean radius, so could we use that?
Huh?
It says mean radius.
That's fine. That's the average radius. That's perfect.
Did you want it in miles?
We need it in what units?
Meters.
Use the units for big G. Meters has to cancel, so we'll need it in meters. And then the mass of Jupiter has to be in what? Okay, please look it up, those of you chilling.
7, the radius.
Radius, please. In meters? 71 million.
492,000.
All right. And that's meters. All right, so you folks are going to put that for radius. What about the mass of Jupiter?
1.898 times 10 to the power of 27
Kilograms. All right, and you can see the radius is really 7.1 times 10 to the 7. Did I do that right? Would you please check my work there? And now you folks can tell me the acceleration due to gravity on Jupiter, right? Go ahead and do the calculation for me because I don't have a calculator handy. So little g for Jupiter. It should be much larger than here, I'm guessing. And then you got 6.67 times 10 to the negative 11. The units are, what are the units for G? Newton meters squared per kilogram squared. The units on your reference sheet are kind of wonky. I use my units for G. I figure them out based on universal law of gravity. Did you see how I got newtons times meters squared divided by kilogram squared?
No.
Okay, look at the top, the numerator in our universal law of gravity. I know G is going to have units to cancel that mass. So the denominator of the units to cancel with the mass of the planet times m1 has to be G squared. No, has to be kilogram squared in the denominator of the units for big G. And then the numerator of the units for big G have to be what? To cancel with r squared. So to cancel this, I need meters squared. So my units have to be meters squared over kilograms squared. And then my units all cancel. And then I just put a newton in front. That's what that newton is. So that's how I figured out my units for big G. That's kind of how I do it. Again, the units they have on your reference sheet are a little bit bizarre. Not as easy to work with. It doesn't cancel so easily. And then what's the mass of Jupiter, please? Again, you're going to put that here. And then you're going to divide by the radius. Sorry, yeah, you're going to divide by the radius twice. Right? So go ahead and do that, please. And I'll be waiting. So I would rearrange it. Jupiter equals 6.67 times 1.898 times 10 to the 27 times 10 to the negative 11. If you're having trouble, I'm sort of organizing it up there. And then I divide by, what is it? 7.1. 7.1. And then I got 10 to the 14. 10 to the 14. All right. G Jupiter 6.67 times 1.898 times 10 to the... What's 14 added with 11? What's that, 25? So I'm left with a 10 to the second. And this is over... Are you guys getting it yet? Tell me what you got, please. I sort of simplified it up there if you're having trouble. I like using this logic of exponents. I don't know what the rules are called, but I add the exponents when I'm multiplying base 10 numbers. I subtract them when there's a negative, and I subtract, like 10 to the 14, I subtract 14 from my exponent base 10 in the numerator. That's how I got 10 to the second. 27 minus 25, right? Because 14 plus 11 is 25. Are you guys cool? What did you get? 24.76?
I got 25.11.
25? You can look up the acceleration due to gravity on Jupiter. I thought it was much larger than that. Something might be wrong. Yeah, Alexa, what'd you get?
Oh no.
Sorry, haha.
I got like
0.25? Okay, so something's clearly wrong here. Maybe I didn't manage my exponents well. Can you please check? And check your own work. Is the acceleration due to gravity on Jupiter only 24?
24.7.
I thought it was much larger. It's only about double here on Earth. Double and another half. Did you guys look it up too?
24.79. Yeah, meters per second squared.
Were we close?
Yeah, we were like right there.
Are you guys all good with this? So that's kind of a nice little problem. I'll leave that up. What'd you get again? Could you read that to me?
We got 25.11.
So it's about 25 meter per second squared. Hey, quick question. If I asked what the gravity field strength was on Jupiter's surface, what would you say? What's that, 25? 25 what? Instead of the meters per second squared, then I would use the newtons per. So you should know that those two units are equivalent, and you should know them. Your reference sheet, unfortunately, doesn't have any mention of gravity field strength. So it's something you should know. I don't think people commonly use it, so it could be something I made up. Just thought I'd let you know. But it does make sense. It's how strong the force of gravity is for every kilogram of mass. It's the strength of your gravity field. Are you guys good? All right, I'm going to post that for you.